So now what we're going to do is we're going to turn our attention to a couple of case study examples, or one case study example with a couple of parts, that will illustrate how to use back pressure related mechanisms in Project Reactor. And part one of this case study is going to apply a bunch of flux operators, like the ones shown here, to create, multiply, and display big fraction objects asynchronously in pool of threads. This first example does not apply back pressure at all. It's kind of the baseline for what comes next. This also shows a couple of interesting examples of monos and how they can be used in conjunction with fluxes just for fun. And it also shows how to create and use a generic blocking subscriber that can be applied to work around the lack of a blocking subscribe operator in Project Reactor Flux. In contrast, RxJava does have a blocking subscribe operator on its observable and flowable classes, so it's actually a little nicer for the purposes that we're going to have to write our workaround here with the blocking subscriber class. So let's go ahead now and look at the implementation. So here we are in the ex4 example in my GitHub repository. And if you go here, you can see we have this entry point class that registers a couple of methods. Actually, it registers 3 methods under test. They are a little bit long-winded in their names. Test fraction multiplications blocking subscriber 1, test fraction multiplications blocking subscriber 2, and test fraction multiplications back pressure strategy, which I probably should call overflow strategy. And you can see here that, as usual, we register these things. We use the task barrier to run them all in the background, and we have the main thread wait for them to finish. So let's go ahead and take a look at the first one of these guys. And we're going to cover some other stuff here. So this first discussion will be a little bit longer than the next two because we want to cover some background reusable classes. So what we're going to do is we're going to start by making ourselves a big fraction array with a bunch of big fractions. These are big reduced fractions. We're then going to go ahead and make ourselves a blocking subscriber. And I'm going to just talk about this briefly, and we'll come back and look at it in a second. So blocking subscriber is going to allow us to wait for, allows the calling program to wait for all the asynchronous computations to complete. And we'll look at this in more detail in a second, but we pass in a string buffer, a size that says, I am not back pressure aware, and a true that says log everything that we are going to be generating. We'll come back and look at this method in a second. We then go ahead and generate a single random big fraction using from supplier on mono, and then we use the mono flat map many method to take that random big fraction and then generate a stream of big fractions from our big fraction array, which was this guy up here. And then for each of the big fractions in the big fraction array, we're going to multiply that random big fraction by each of the big fractions in the array using the Project Reactor flat map concurrency idiom, and we're going to do all this stuff in parallel. And this is what the code looks like. It's very simple. We simply multiply the big fraction by the other big fraction, and we do that in a background pool of threads, which is the parallel pool. Then what we do is we go ahead and subscribe. So remember, subscribe is kind of like a terminal operation in streams in the sense that it kicks everything off. Nothing starts to run until subscribe is called. And we pass in the blocking subscriber. And we're going to look at that in a second. This call here will return right away because it's asynchronous. But we call blocking subscriber await to wait for all the asynchronous processing to be done, at which point this call will unblock and return. So this is our workaround for the lack of a blocking subscribe operator in Project Reactor Flux. So now that you've kind of seen the overall flow, let's go take a look at what blocking subscriber is. So there's a factory method called make blocking subscriber. And what it does is you can see it's going to make a blocking subscriber. And it does this by creating a new instance of blocking subscriber. And here's what blocking subscriber looks like. It's a class that inherits, or rather implements, the subscriber interface. And you're not usually going to need to do this, so IntelliJ will warn you about it. I turned off the warning because I know what I'm doing here. But normally you don't do this, but we're doing it here because we want to make our own blocking subscriber. And you'll see we have a whole bunch of fields. We have fields that are going to keep track of the consumer to invoke when we get the next on next value successfully, the consumer to invoke if we get the on error signal, the runnable to invoke when we're done with all the events, if we're done, which we will be, an integer that is used to indicate how many requests should be sent by the upstream publisher, and this can either be something like long or integer max value, in which case it says send everything, don't do any kind of flow control or any kind of buffering or whatever. Not buffering, don't do any kind of back pressure aware behavior. But if it's less than the max value, it will only send that many events until prompted to send the next one. We keep track of a debugging string buffer. We keep track of the subscription we get from the publisher, because we're going to need that when we need to ask for the next chunk of data. We have a couple of atomic integers, which we use to keep track of the number of events processed within a chunk, as well as the total number of events. And then the last field we have here is a countdown latch, which is a cool Java synchronizer that can be used to allow the calling thread to await for all the asynchronous processing to be done. And you'll see how that gets used in a second. There's also a constructor here. The constructor basically takes the consumer and runnable parameters, the value we want to use for the requests that we're sending upstream to the publisher, and the string buffer. So we initialize the fields, and then we make the countdown latch have an initial value of 1. So that's what happens when we're creating a new blocking subscriber. And now you can see when we actually make one of these things, we're giving it a lambda expression to handle the on next event, which is just going to append the result to a string buffer. We have a lambda expression to deal with errors, which is just going to say we're done, display the string to this point. We have a lambda expression to deal with successful completions, which also displays the string that we've been building up to this point. We pass in the request size and the string buffer. So now that you know what we're passing in here, we can return back to blocking subscriber and look at its other methods. So here is the onSubscribe method. This is the one that gets called back automatically by the publisher when the subscriber subscribes. And you can see it passes in a subscription object, which we stash away. And then we do our initial request. We say, I want this many events sent to me before you wait for the next request. For this example, we're passing in the max. So we're going to get to send them all in one fell swoop. Here's what onNext does. You can see it calls the consumer's accept method to do whatever we wanted the consumer to do, which in this case was to put something into the string buffer. And then we do a little fancy footwork here. We increment the total number of events we've seen, because we want to keep track of that. And then we also increment the number of events we've processed thus far. And if that equals the request size, that means the publisher's not sending us any more data until we ask for it. So what we do is we put a little logging message in our string buffer just saying, hey, we're requesting the next chunk. And then we ask the subscription object, please send me the next chunk. So it'll start with the next chunk. And then we set our events processed thus far back to 0. The error handling stuff, when we get an exception, if for whatever reason we log what the exception was using this cool technique to ask the exception, what was your name and what was your message? Then we handle the exception, which in this case is going to shut down, it's going to print the string buffer. And we release the countdown latch, because that means the caller can proceed because we're done. The onComplete method is similar, except this time we've succeeded. So we print the number of events that completed successfully. We execute the runnable hook method here to wrap things up, which in this case will print the string buffer. And then we release the latch there as well, so the caller can proceed. And then down here, we just have the count of the total events. And finally, the await call. The await call is the call that the calling thread will use to block until all this asynchronous processing is done. So you can see what it does in this case is it awaits the result. And when onComplete or onSignal is called, the countdown latch is released, thereby allowing the caller to proceed. OK, so that's basically walking through that program. Let's go ahead for kicks, and we'll run that first program, that first test. I'll stop as soon as it's done. Well, I won't stop. I'll let it run, because we can use those other results for later. But you can see here that what's happening is it's generating the results. And you can see that didn't take very long. And so what we're getting here is basically, it says start asynchronous processing. waiting for async processing to complete. These are the results of doing all the asynchronous processing, and we succeeded. So 8 asynchronous computations completed successfully. So that's good news. OK, so that's the end of the first example. Notice there is no flow control here whatsoever, or back pressure.